Okay, welcome back. This is the second part of the final topic in the course, which is some problems now off of old public exams that are relevant to fission, fusion, and nuclear power. Okay, so let's take a look at some of the questions that have shown up on old publics in relation to these topics. Okay, here's the first one. This one is a fairly easy question to do. E equals mc squared. Okay, E equals mc squared. That is the theory of relativity, essentially. The relationship between mass and energy. That's Einstein's equation. And I've said before, probably the most famous equation ever in physics. That's the one that a lot of people have heard of for sure. So the mass is given. It's 4.37 times 10 to the power of negative 25, multiplied by c squared, 3.00 times 10 to the power of 8 squared. Okay, you do that calculation, you will get this answer, 3.93 times 10 to the negative 8 joules. That's how much energy is released when that much mass gets converted to energy. In other words, if that was the mass difference, or the difference in the reactants and the products, that is the amount of energy that would get produced in that reaction. Then the second one talks about nuclear fusion. Which one best describes nuclear fusion? Now remember, nuclear fusion, first of all, is very high temperatures. And when I was talking about fusion back in the first half of this, I said that very, very difficult to contain. Just picture the damage, the destruction that a nuclear weapon causes. Okay, very high temperatures, and of course because they are very high temperatures, they are very difficult to contain. Okay, that's one of the features, one of the fundamental things about fusion. It's one of the reasons that we have not been able to build a workable fusion reactor yet. It'd be nice, it'll be great when they finally get to do it, because it'll be a very, very good fuel source, energy source, but at the same time, it won't produce all these harmful radioactive isotopes that are produced in a fission reaction. So that's the answer. What is the purpose of the moderator surrounding the fuel? Remember, we said moderator doesn't absorb neutrons. That's the control rods do that. The moderator is designed to decrease the speed of the neutrons, and by slowing them down, we ensure that they can be captured by a nucleus of uranium. Okay, so it's to decrease the speed, not absorb neutrons. No good to absorb them. If we absorb them, the reaction will stop. We just want to moderate them. Moderate means even out, right? Slow things down. Let's try this one. This diagram shows part of a typical chain reaction for uranium-235. This is typically what happens inside the CANDU reactor. So one neutron enters into the nucleus of a uranium atom. So neutron bumps into the uranium atom. In the process, we get barium and krypton, and 1, 2, 3 neutrons being formed. Okay, if you look carefully at the choices, this is the only one that shows that. If you look carefully at B, you'll notice that B had one little difference. It had a proton instead of a neutron. See that? Proton instead of a neutron. That was the main difference in that one. And C had the 4 neutrons on the other side, but that's not right. The neutron is on the same side as the uranium, then all these things form from that. That's why it's A. Let's try this one. Given the information in the table here, how much energy is emitted in this reaction? Well, anytime you want to find energy, you always have to do this first. You always find the mass difference first. And mass difference is always equal to the reactants. I'm going to write it down like this. Reactants minus products. In other words, the left side minus the right side. So what we've got is 22.9945 take away what's on the other side, which is the sodium, 22.9898, and 0.00055. Okay, do that calculation, and here is what you will get. 0.00415. Use. Now, if you remember back to another topic, we talked about this earlier. That is one of the possible units that can be used for mass. Okay, kilograms is one. Those U's, or unified atomic mass units, is another one. And there's a third one as well. And in this case, the third one is going to be the useful one. Here's what I'm going to do. I'm going to multiply by 931.5 mega electron volts per C squared per U. That's my conversion factor. That conversion is straight off of your formula sheet. It says 1 U equals that number of mega electron volts per C squared. That'll give us a different unit for mass. That will give us this unit, 3.87 mega electron volts per C squared. Now right now that's a mass unit, not an energy unit. But in order to change it to an energy unit, all I have to do is this, E equals mc squared, which means I take my 3.87 MeV per C squared, and I multiply it by C squared. When I do that, the per C squared and the C squareds cancel, and I'm left with 3.87 mega electron volts. The answer is A. That's the easiest way to do it. If you want, you don't even need to write in this step right here, because all you got to do is cancel out the C squareds, and you know you got the energy anyway. 3.87 mega electron volts. It's always easier to do these when your units are U's. When it's in U's. Always easier, because it's a very simple conversion. All right, what is the mass defect of a fission reaction if it releases that much energy? Well, remember, energy equals mc squared. Einstein's equation. I can rearrange that to find mass by saying E over c squared. Okay, you're given the energy, 2.9 times 10 to the power of negative 11. I have to divide that by 3.00 times 10 to the power of 8, all squared. That's c squared. Don't forget that squared. That's very important. And when you do that, you will get this number, 3.2 times 10 to the power of negative 28, and that's in kilograms. When you do the E equals mc squared calculation, using kilograms for the mass, you get joules for the energy. So because we were given joules for the energy, we know the mass must be kilograms. If you get mega electron volts for the energy, then you know it was the other unit of mass, okay, the MeV per C squared. Anyway, that answer is A in this question. Okay, again, pretty simple calculation. Let's try a couple more. Which of these would be classified as a nuclear fission reaction? Well, in a fission reaction, a heavy nucleus splits into two lighter ones. Okay, so it's either A or B. Okay, we don't have smaller nuclei joining, that's fusion. Then it says energy is absorbed or energy is released. Well, remember, fission reactions release huge amounts of energy. We said that, right? If it absorbed energy, it wouldn't be much use as a power source, would it? Energy is released. It's B. What's the function of control rods in a fission reactor? Well, remember, the moderator was to slow down the neutrons. The control rods, they're supposed to absorb neutrons. That's their function. Absorb neutrons to control the rate of the reaction. That's how that one works. Then we've got the last one, and again, it's giving us a mass, but it's telling us the mass of the products is that much less than the reactants. In other words, that is the mass difference. That's the mass that went missing. So therefore, that missing mass was converted into energy, and we can now see how much energy was released by using this calculation, E equals mc squared. So we got 3.2 times 10 to the negative 28. We multiply that by 3.00 times 10 to the power of 8 squared. And if we do that, we get this answer, 2.9 times 10 to the power of negative 11 joules. And that doesn't sound like a whole lot of energy. But remember, that's from just one reaction. That's from one nucleus splitting. Remember, there's billions of nuclei splitting every second. So there actually is a tremendous amount of energy there. Tremendous amount of energy. Let's try this one. Energy released in this reaction. Now, the masses are all given in U's. In other words, unified atomic mass units. So the very first step is to calculate the mass difference. We need to calculate the difference in the mass of the products and the mass of the reactants. We subtract reactions minus products. And that equals this. We just took the number straight at the table, right? We got a lithium ion up here plus a neutron. So we take the mass of the lithium ion and the mass of the neutron and plug them in right here. Then we subtract the mass of the products, which was helium and hydrogen. Two of those right there. And that will give us this number, 0.00516 U's. Now you got a choice. You've got two options. U's are not going to be any good for energy. In order to calculate energy, I need to have either kilograms or the mega electron volts per c squared unit. One or the other. Now the easiest way to do it when you have U's is to convert that into the mega electron volts per c squared. Multiply by 931.5 to get 4.81 mega electron volts per c squared. And then you plug that into E equals mc squared, or you can just cross off the c squared. It really doesn't matter. You'll still get full marks for it. And that will be 4.81 mega electron volts. That answer right there. Now, you could also come back up here, convert that to kilograms by using the conversion factor on the bottom of the formula sheet, which is 1.6605 times 10 to the negative 27, I do believe. You multiply by that to get kilograms. Then you'd say E equals mc squared, and if you use your mass in kilograms in that equation, you'll get joules as your units for energy. Okay, that's just as right. The only reason I did it this way is because that's easier. Now, if you happen to come across this one on the old public, you'll notice the solutions they did, they actually did convert to kilograms and get the answer in joules. But like I said, it's much easier to do it this way. Trust me. That's a lot easier. And if it doesn't tell you which units to use, it doesn't matter. You can use either. You can use any unit you want as long as it's an energy unit. Let's try the next one. Another mass difference calculation, only this time you'll notice all the masses are actually given in kilograms. So when the masses are given in kilograms, it's easier to stick with kilograms. So there's the mass before, there's the mass after. So in other words, mass of reactants, mass of products. All I got to do now is find the mass difference, subtract them, and I get that amount right there. 3.14 times 10 to the power of negative 29 kilograms. That is the mass difference. In other words, that is the mass that gets converted into energy. Now, because it's in kilograms, it's easier to leave it like that and use E equals mc squared, mass in kilograms times the speed of light squared, and you'll get your answer in joules. 2.83 times 10 to the negative 12 joules. Now again, you could convert those kilograms back into U's by dividing by the conversion factor and then multiply by 931.5. That's okay too. Whichever thing you feel more comfortable doing, it's fine. Both are right. Both are correct. All right. Sometimes this type of question shows up. It's only been there once or twice, but you never know. Two arguments to support or two arguments to oppose nuclear energy production. Now, we just went over those in the last section. Like, to support, for example, it's a nice, clean fuel as opposed to fossil fuels. It doesn't produce greenhouse gases, for example. Okay? It produces large amounts of energy, is another positive one. The CANDU reactor has a very good safety record. There's another positive. Okay? Two arguments to oppose. You could say things like there's the risk of a nuclear accident. There's the problem of what to do with the radioactive waste that's left over. Okay? There's the problem of the nuclear power plants being extremely expensive to build because there's so many safety things had to be built in. There's the problem of the mining. Remember, mining of uranium can release harmful compounds into the soil and the water. Okay, so there's a whole bunch of different ones. And if you can't remember them all, you can just go back and look at the